We've been talking about kinetic molecular theory and gases and how they behave. And some of the things that the kinetic molecular theory says is that gas particles do not interact with each other. They're not repelled or attracted by each other. And there's a lot of distance, a lot of empty space between them. And so under most conditions, gases behave in that way, and they obey the gas laws. And on the left is an illustration of ideal gas conditions. So here's fairly high temperature and low pressure. And so at a low pressure, there's lots of space. At a high temperature, these particles are moving quickly. And so when they do collide with each other, they don't really have time to interact at all. If we cool the gas down and compress it, then we begin to see non-ideal behavior between the gas particles. This is low temperature, high pressure. When we cool the gas down, the particles are moving slowly, more slowly than at high temperature. And there are attractions between gas molecules. They're just generally insignificant. You can think of those attractions as being a little bit like Velcro. And, you've probably all seen those inflatable Velcro walls, and you put on a Velcro suit and you jump up and you stick to the wall, and it's like, wow, that's cool. Never done it myself, but it looks interesting. But, we all know what Velcro's like. So what if you had people dressed in Velcro suits, the kind that would attract each other, stick together? So if you had a Velcro suit on and your neighbor had a Velcro suit and you just walked and bumped into each other, you would stick to each other, right? If you were moving slowly. If you ran at each other at high speed, you would probably not stick to each other because you're going so fast you'd kind of bounce off. It's a new analogy. You don't like it?
I don't think that would happen.
You don't think it would happen?
They'd still stick.
Okay, let's think of,
Let's go 40 miles an hour.
40 miles an hour, yeah.
Don't
Probably
stick any longer.
splatter.
They might die.
So, they would
So let's think something hard and round, large bowling balls or something in Velcro. And if you run them at each other slowly, they're going to stick. And if they go fast, it's an elastic collision, and they're maybe going to stick a little bit, but they're not just going to go and stick to each other because they're going so fast they're still going to bounce off of each other. Is that better? A little bit? Not
Still
much. Still.
Okay. I want to see it.
Okay, let's
You need a
move.
stick figure drawing.
Yeah.
Let's bring Velcro suits.
Okay, so let's
No, he gets it.
let's.
I get it. I just think that it would still work because it's Velcro. You've never done the jumping, right? You know how strong Velcro is.
Well, no, Velcro is very strong, unless you only have a little tiny piece of it, and then it's not so
So
strong.
let's imagine they barely touch and they go. I can understand that.
Well, yeah, the attractions are weak, and then it's going so fast. So maybe it'd be better if it was just a little patch of Velcro, and you were running past someone and you wouldn't even really notice that it kind of pulled on you. Whereas if you were walking slowly, then you might notice it more. Is that better?
Yeah.
Okay. Because, you are the ultimate approver of the lecture, right? Yeah.
Yes.
Okay. So when the particles are moving slowly at low temperatures, then when they bump into each other, they stick to each other a little bit. And that messes up this ideal behavior that they have. The other thing that happens is when they get all squished together like this under high pressure, now the amount of empty space between them is going down. And so then the volume of the particles themselves starts to become a little more significant. And you can imagine that if you keep squishing it together and you keep cooling it down, you're going to end up with a liquid. Does a liquid act like an ideal gas? No, it's not even a gas, right? So the ideal gas laws work over a certain range of conditions, but at the extremes they break down. So that's all that was about. It's a lot for nothing.